Okay, hello everyone. Thanks for joining this webinar. We're going to be discussing about risk modeling in cardiomyopathies. And this is going to be slightly different than the previous heart muscle talks we've done before. So this is not an abstract or a lecture, it's more of a moderated discussion. We're very glad to have Dr. Menelaos Pavlou, who is he has been our collaborator, but he's an expert statistician. He works for the Department of Statistical Science at University College London, and we also have Max Lorenzini and myself. So we're really looking forward, just even for the discussion between ourselves, just to learn more from Menelaos. I'm just gonna put up the slides. So the slides are not gonna be. It's not a lecture, as I said. It's just more kind of to guide us through the discussion and visual aids for the discussion. We want people to submit their questions or their comments, and we will address them directly and not at the end. So we will try and spread out all the points throughout the hour. So any questions you have that might be relevant, even for points that we will discuss later on, or for points we've discussed, please feel free to do so. I know anything from Max or Menelaos before we start?
Well,
Yeah.
I should say thank you for inviting me to be here. Thank you for the opportunity from your group that you have given me working with you for so many years. And yeah, I've learned a lot during the process. And yeah, so I'm happy to give back some of them.
Awesome, Menelaos, thank you. So this is pretty much the summary of the points we will try and cover. So we'll talk about, I mean, when we say risk, we're mostly referring to sudden cardiac death risk. In most cardiomyopathies, this is one of the key elements of patient management, is deciding who should have an ICD. And, since pretty much the hypertrophic cardiomyopathy risk calculator, we've moved, from just using risk factors 1, 2, 3 to a more complete solution of a risk calculator. So this is kind of very, very relevant for research and for clinical practice. We will go through the parts that is, how do you actually create one, and how do you validate one, and what are the key things to look into, a calculator has been already published, and what are the, the limitations and the caveats. How do you improve one, for example? And then we will discuss some more kind of practical points on their application in clinical practice. The caveat is, prediction is quite difficult, especially if it involves predicting the future. So whatever we say here today, this kind of is the main truth. And here I have some slides for just as an example of calculators. We have the ARVC risk calculator that I have been involved in trying to validate. Essentially, the idea is that you have a multivariable model that has been created, and then you're able to provide information for your patient on all those variables, and it will give you an estimation of whatever the outcome is. In this case, sustained ventricular arrhythmia, for example, at a certain time point. And you can use this in your clinical practice. A more well-known one is the hypertrophic cardiomyopathy risk calculator, that's been out since 2014. And I think most people joining this session might have used that. And this is the point where, when you see this, you start to think that you need a statistician to be around. I don't know, Menelaos, you want to start by just trying kind of to tell us what does that say here?
Yeah, sure. So I think in the next couple of slides, we are going to say how we build a model. And well, this is kind of the end product. So I will briefly get you through the process. So we have an outcome that we are interested to predict. It could be a binary outcome. It could be a yes or no answer. For example, die in hospital after an operation, or it could be a time to event outcome, as we have here. For example, sudden cardiac death at 5 years from, say, diagnosis. So, and you as expert, clinical expert, have a very good knowledge about what are the patient characteristics that are likely to affect the outcome. And Alex mentioned that in the past, we used to use those score systems where each factor was given, used to be given a point or two, and then would sum them up and come up with a final score. Well, you can see this equation that you can see here is kind of an extension of that principle. So the idea is that we have different predictors that may help us to predict the outcome. And by using statistics, we kind of calculate how much weight does each predictor takes. So the numbers that you can see in that equation is, well, the weight given to each factor. So that's what a statistical method does essentially. Calculates the weights for each predictor. Okay, that's I will have to say that this is this, for example, is a Cox proportional hazards model, if I remember well. So for time to event data, the outcome is time to event. Cox model that many of you may have heard is a popular, a common way to estimate these weights. If I had binary outcome, so yes or no death, for example, within the hospital after an operation, there would be a 0-1 outcome, and I would need to use, for example, logistic regression, right? So logistic regression and Cox regression, in this case, are the methods, the tool I use to calculate those coefficients. The coefficients are the numbers that you can see in that equation. So it's a big equation, but it's actually not very complicated, really. So that says equation E. That equation says if you provide numbers for maximal wall thickness and left atrial diameter, etc., then I will make a calculation for you. Okay, so we use statistic here to kind of get the optimal weight that should be given to each of those predictor variables. Optimal weight in the sense that it optimizes the predictive performance.
Yeah, that makes sense. And you know, as we move towards discussing how do you actually develop a model from scratch, I think it's worth just explaining again that, you know, your outcome can be a specific event that happened, yes or no. So for example, sudden cardiac death. But in most of the models that we use, at least in cardiomyopathies, we are interested in the time to event. So we don't just want to know if the outcome happened, we want to know how far since the baseline it happened. And that is slightly different, and that's where, you know, Cox regression, survival analysis comes into play. So the standard, you know, the standard way of creating a data set would be that, you know, imagine that the rows, imagine a table where the rows are each patient and columns are variables. And, you know, you have your predictors, like, let's say, for example, AIDS, weight, left ventricular ejection fraction, whatever else you might think of. And then you have the outcome, let's say sudden death, yes or no. And then you have a time variable that is since the baseline, when did the event happen, or when was the last time that you saw this patient and they did not have an event. That's kind of the basic structure of a data
exactly,
set.
Alex. So like in shorter outcomes, the outcome can be sort of thought to be a yes or no outcome. That would be, for example, in-hospital mortality after an operation. That is short-term outcome where logistic regression may be suitable. If you are looking at then diseases where we follow up patients for a long time, for example, in cardiomyopathies, then it takes for a long time for the adverse outcome to appear. That's why we are interested not only whether it happened or not, but at the time where it happened. And that's where Cox regression comes in. Right, so that's kind of the first. When I talk with a clinician about any given study, really, my first question is, what is your outcome? So that I know what I'm going to have in the left-hand side of an equation that I'm going to use a statistic to derive. Right, so that's a very important part. Now, that equation that Alex showed before was based on Cox regression. You may have heard recently, or you may go back to the next slide, Alex. So there are some fashionable new techniques, or maybe not so new techniques. AI techniques, some people call them, others call them machine learning techniques. These can also be used to estimate this association between the outcome and some predictor variables, but they don't do that in an as simple form as having an equation. It's more of a black box approach. And sometimes it's a good idea. Sometimes it may not be a good idea. I think we have some slides, Alex, that come later.
Yep.
I don't think we should spend time on that right now, but we can revisit later.
Yeah, for sure,
yeah?
for sure.
So machine learning is something that's coming up a lot. At this moment, I will say maybe it's not always a great idea in this context, and we'll come back to it later. So not on the idea, well, my opinion is not go to an AI approach just because it's more than a cool thing to use.
Yeah, 100%. So, I mean, what we're trying to say is that when you use methods like Cox regression, you can have an equation, well, a function like this, which actually tells you, how do you estimate the probability? And I think that's, it's super important that any paper that comes out, with such a model, they should be showing this function, because that tells you exactly, what the model is. There have been some cases where they haven't published, for example, this, and I find that quite frustrating, because you can have an online calculator, but you want to be sure that the calculator is working properly, and then when you do a validation study, you're going to use this to do the estimation. So yeah, it's tricky. I think now we can talk a bit about validation. So when you have a model that's been when you're developing a model, when there is a model that's been published, that's not really kind of the the end of the story. You need to know how well the model performs on data that it wasn't trained on. Because if you're just validating on the data you used to develop the model, then it would make sense that if you've done a good job, then it should work. Is that right, Menelaos?
Yeah, that's correct. So I have some data. I use some cool statistical way to estimate those weights, those coefficients that I mentioned earlier. And as a statistician, I'm very happy about that. But then what's important is to see that what I actually estimated will indeed result in good predictions. Good predictions when I use the model to predict in a new patient, right? So sometimes, as we're going to see in a bit, if I have too little data to develop my model on, then what happens is my model is kind of very adapted too much to the data that I have in hand, right? So then what happens if I try to apply that model in a new data set or a new patient, it doesn't do as well. And that's called overfitting. And that's receiving a lot of attention recently, but also
For sure.
the last many years, really.
Sure.
Right. So I want a model that can predict well in new patients.
New patient,
right?
yeah. So in terms of the validation, there are two key things to look into. One is the discriminative ability. So how well can the model differentiate those who will have the event versus those who won't? And the other one that we'll see on the next slide is the calibration in terms of being able to predict, the probability being close to reality. So I'll just quickly describe the discriminative ability. So imagine all these data points are patients. This is quite a metaphorical, not an actual data-driven graph. But essentially, you want a model that, if the oranges are the ones that will get to the event and the blues are the ones that won't get event, you want a model that's this line that is able to perfectly separate those two and, without any overlap, and tell you that these people will definitely have the event at the time point that you have set. But in reality, you never get that. This is I don't know if it's statistically feasible, Menelaos, but it seems to be quite difficult.
Indeed, yes.
And this is an actual example. So this is from our ARVC risk score validation study we published about 2 years ago, where imagine that at the bottom you have the 0% 5-year risk based on the model, and the top you have the 100%, and then if you lay over all the patients in the different levels of predicted risk, and if you mark the ones that had the event with orange, this is what you see. So of course, most patients are at the bottom. Most of them have a low risk. That depends on the overall prevalence of the event in your study, of course. That's not true for every cohort, but for ARVC and sustained ventricular arrhythmia, this is how it looks. And then as you go on the top, you see that the oranges are proportionally more than the blues, which means that you're on the right track in terms of discrimination. But you need some measures to tell you how much is it. How can we quantify that? One way is to do receiver operator characteristic curves, where you get the area under the curve. Menelaos, do you wanna kind of talk through this?
Yeah, so I mean, I can start with the question. So many people have heard of AUC, which is similar to the C index here. Does anybody know what kind of values does it take? Here, Alex said is 0.75. Would you be able to say, was that a good value or a bad value? What do you think?
Max, you have to answer this one.
We can say, I can take this one because, well, it's pretty good because we know that if it were along the line cutting down the middle of 0, that would be effectively no different from chance. And if it were equal to 1, it would be perfect ability to predict the outcome. And so 0.75, it's not bad, but it's not perfect. And
yeah,
well, that's what it looks
sounds
like.
Yeah, sounds about a convincing explanation to me. So yeah, the C index or the AUC, it's a measure that of discrimination. It usually takes values between 0.5 and 1, where 0.5 means no discrimination and 1 means perfect discrimination. So, and it's also a probability, right? So is a probability, so my model gives me some probabilities, right? So this C is the probability, given that I have 2 patients in front of me, this C index is the probability that I assign the highest predicted risk to the patient with the longest survival time. Sorry, the other way around. The lowest survival time. Okay, so and if I achieve it every time for every pairwise combination of all the patients in my sample, then I get a C index that is 1. if I achieve, if my prediction is the same as tossing a coin, then I get a C of about 0.5. Now, I wanted to bring up a few other points here. So sometimes it is said that C index or AUC reflects the predictive strength of my model and the strength of the predictors. And that's true. And how I think about that is I have some predictors that may be good or not very good. And by having more data, I estimate the association between those predictors and the outcome better. So, and by doing that, the C will be growing with bigger size, but and that's the important thing, it will plateau. It will plateau at some point, and that would depend on how good my predictors are. So, for example, in this example that Alex presented, if I had a model with only age and sex, even if I had all the data in the world, that wouldn't be enough for me to discriminate well. So even if I estimated the association between age, sex, and my outcome perfectly, because I have all the data in the world, still my C index possibly would plateau at 0.55, something like that, because that's how strong my predictors are. On the other hand, as I start bringing in better players, so if I start bringing some cardiac measurements, maybe some genetics, etc., then my predictors are stronger. So the C will grow, right? It might never go to 1, right? But it will grow. If I have good predictors and I have enough data to estimate their association with the outcome very, very well, then I kind of my C index will reach its peak. Right? So it will be as high as it can for this set of predictors. So
that's a very interesting point. And so how do you know when you're reaching that plateau? So how do I know when to accept that my model is reaching peak performance and it's no point in adding thousands of other patients? Or
so that relates. Thank you. Yes, that's a good question. So that relates to the sample size calculations that we're going to see a little bit later. But the answer is it plateaus when you collect infinitely large size. So you will never do that, right? So what we are going to see, we try to find a middle point where, say, if my C index in this example plateaued at 0.778, I'm prepared. If I had infinite sample size and I would estimate the association between predictors and outcome perfectly, I am prepared to use 1,000 patients and sacrifice a little bit about in terms of that discriminatory ability. Okay, that's how we think about it.
So just to summarize for everyone, what Menelaos has described is that as you try to improve the discriminative ability of the model, so as you're trying to separate those orange and blues, one thing you can do is, based on the set predictors you have used in the model, you can increase your sample size to a certain point where to maximize, let's say, the benefit from these specific predictors. But after a certain point, it doesn't matter if you have this many or a million more patients. It wouldn't make a huge difference.
Exactly.
And that's the point where you need to start to think, can we find better predictors instead of trying to do this? And then, of course, it depends on the clinical setting. If you have a rare disease, it's not always very easy to get more patients, but you might be able to find better predictors. So, So here we saw one of the measures of the performance of the model. But imagine if in this actual model, actually the blues and the oranges were completely separated. That would be perfect. But is that all that we need to know in terms of the model validation? We need to know something else as well. We need to know, those numbers that we get from the model, whether they are close to reality or not. If the model tells you 10%, would you expect to see let's say an actual probability or an actual rate of 10%, or is the model completely off? Because even if it had a perfect discriminative ability, you still need to know this piece of information before you use it in practice. This is I'm just going to go through this. So this is again from the validation of the RVC risk calculator we did, and this is a calibration plot, as it's called. On the y-axis you have the fraction of the positives, and on the y-axis, on the x-axis, you have the predicted probability. So what we've done is we've grouped our cohort into a certain number of groups so that they are sufficiently large to be able to look into each one. And then we have calculated what is the predicted probability in these patients, and we have also calculated the event rate in those groups. So we're trying to see in each group how much we predicted, how much we actually saw. And you should expect that a perfectly calibrated model falls on this red line here. So if you predicted on average 50%, you see an event rate of around 50%, for example. But what we actually saw in this model was that we were getting much higher predicted probabilities than the actual event rate. So, for example, the most kind of edge case was this group here had a mean predicted probability of around nearly 50%, but the actual estimated event rate was just above 10%. So there's a huge discrepancy between what we were expecting and what we actually found.
Alex, this job of checking prediction and actual events, can you do it in your original cohort that you used to derive the model, or do you need a completely different cohort of patients that weren't involved in the model development?
I think Menelaos, you should answer
that. Yeah, well, you can do that. And definitely something you can do. The thing what it will happen most certainly is that all the points will lie on that red line. And then you will be very happy that you have a really well-calibrated model.
If you've done it on the data you've trained the model, you mean? Yeah.
Yes, that's it. Yeah. So you can do it, but you shouldn't be doing that, because that relates to the way this association between predictors and outcome is calculated. So this calibration plot should be estimated, should be calculated on a new validation sample, right? And so essentially what we are looking is whether the estimated probabilities are the same as the actual proportion of events at a given time point, right? So very important. Ideally, all those blue points should lie on that red line. Yeah. And so here is a case where those the predicted probability it's to the right, so it's much higher than the observed probability, right? And that's a typical symptom of what we say model overfitting. Model overfitting is that at the extremes, at the high end and low end, sometimes I tend to get values that are too extreme. So and that means that the calibration slope, which is an very important bit here, it goes away from 1. Here it went to 0.5, which is really, really low. So ideally, I would have liked the slope of that blue line to be 1. So have the same slope as that red line. So overfitting means exactly that. My model possibly was, as we say, trained. That means was adapted too much to the development sample. And as a result, when I apply the model to predict, I use the model to predict the outcome in new patients, it doesn't do as well as I would have hoped. Now,
essentially, it's working too well on my data, but not on other data.
exactly. Yes. So that possibly would mean that the data that you had, if you had developed that model, Alex, the data that you have used possibly were of small size, right? You had too little data, right? And as a result, the model was overfitted to that, adapted too closely to that data and doesn't do well. As a result, the calibration slope deviates a lot from 1. Now, what would have happened if you had more data to develop the model on, then the calibration slope would start going up. So if you tripled or quadrupled or have 10 times the size for the development sample, then when you validated the model, then that blue line would start moving close to the red line.
That is, of course, supposing that you have a non-selected population and you're expanding it and don't have a bias in who you're including.
That's a very good point as well, Max. Yes. So assuming that the population that your validation sample comes from is the same as the data for the development sample.
I think that's a key point, because here what we observed. So the group that the model was trained on here and the group that was validated on were quite similar. Ours was a bit bigger, but it wasn't such a big difference. Not enough to be able to attribute this to overfitting. But what we saw is that overall, their patients were having events twice as more frequently than our patients. And one of the reasons we try to attribute this to is that we're slightly different centers. They were more arrhythmia-oriented centers. We are more kind of heart failure, cardiomyopathy-oriented centers. So maybe there are separate, there are biases on which patients end up in each center, and maybe that's why we do observe this different incidence of the outcome, and that's crucial, because when you apply the model, maybe it does matter who is applying the model, because even if it's the same disease, there are significant biases on each center, and on the studies that the studies reflect the biases of the centers included. So it's reality is quite tricky.
Yes, indeed. I would agree with that. So many times it's how the outcome is reported. So even if you have very depending on the disease, even if you have very specific criteria, still there could be deviations. So even if the patients are from the same population, the data are recorded, especially the outcome is recorded in a slightly different way, which may cause the performance of the model to appear not as good when applied to a different center.
So Menelaos, before you delve into sample size, you've clarified very well why it's validation studies are essential in establishing the role and accuracy of a risk prediction model. But the truth is, we all get very excited when there's a new risk model that's published, and you read it and you want to use it, and we're less excited about validation studies. No offense, Alex, but that's the truth. And so when you read the next exciting brand new risk model, is there any way I can understand how good the calibration is, if it's how reliable it is in predicting just based on that model, or do I just have to sit tight and wait for a validation study?
Well, ideally, we should be externally validating models before we start using them. Otherwise, I'm sure you wouldn't be happy applying a model for your patients, and then after a year finding out that the predictions that you are using to make your decision or aid your decision were not as good as hoped. So having said that, also an essential aspect of model development, I would say, is apply some statistical tricks, let's say, to what is called internal validation. That is, validate my model using the same data that I have developed it on, and not a completely new data set. So I use the data, the data that was used for model development, and apply some resampling techniques. So that way you can get an assessment of model performance that wouldn't be possibly as good as an external validation, but it's definitely worth doing. And I think the guidelines are internal validation should always be reported. So even, and I understand your comment because because in many cases we have very rare diseases or very rare events. So waiting to get a validation sample either would take a lot of time to collect data, or a lot of time to bring many centers together to give the data so that we can validate the model. So yeah, definitely that's a good question. Yes. So if you don't have a validation sample, then internal validation can be done. It won't be as good as external, but it's
better than nothing. Yeah. Okay. So we need to make sure that new models include some degree of internal validation.
Yeah, that's a must, right? Any model should be at least internally validated.
Okay.
And there are different schools of thought, really. So sometimes people have data and they'll say, should I keep half of them for development and the other half for validation? Well, that's a personal opinion that you should be using all of your data to make sure you develop a good model and not sacrifice some of your data just to have a data kept aside to validate it. Right?
So
now, if you have a lot of if you have a lot of all the data in the world, then that would be an option. But sacrificing some of your data just to keep for validation, possibly that comes with some caveats.
I think that brings us nicely to the sample size as well, because if you have adequate sample size, maybe you can sacrifice some data.
Yeah.
I think you have already covered this. Is there anything you'd like to stress from this section?
Well, what I would like to stress here is that what we said is that when the sample size is too small, then there is a danger of model overfitting. Well, there is a very good solution to the model overfitting is to get a sample size that is infinitely large. If you have an infinitely large size, then for any set of predictors, calibration slope would be 1 if validated on data from a new population. Nobody would get collect data for the whole population. So the idea here is that having a smaller size would lead us to a calibration slope less than 1 and an overfitted model. But on the other hand, I cannot get an infinite sample size. So how large should my sample size be? Well, the idea behind the sample size calculations are that we should aim to collect enough data such that this calibration slope doesn't go too small. So say a threshold that has been proposed is 0.9. So I will not need an infinite sample size, but still I will have enough sample size so that my overfitting is not dangerously low.
So that means that the team that's developing the model, they can do this testing to see how close they are to this. And
actually, these calculations can be done even if you don't have any data in front of you. But if you have some idea, so if you go to the next slide, Alex. So say you're doing a prospective study, right? And so you need 3 ingredients in order to calculate the sample size that your study should have. So the first one is outcome prevalence or outcome incidence, right? That's something that you should be able to know, right? As clinicians have a very good idea about the prevalence or incidence of the disease. Now, a smaller incidence would mean, as we're going to see in a bit, a larger sample size. So that's one determinant. The next is how many predictors I will have in my model. So again, it's intuitive that if I have to estimate more things, I need more information to estimate those things, and means larger sample size. And then the last part that is less intuitive is that it relates to the AUC or the C statistic or C index. And we mentioned, imagine you knew where your C statistic would plateau for a model. So the higher where the C statistic would plateau, then the smaller sample size you would need to estimate to develop a good model. So that's a little bit counterintuitive, because if you have a model that it will have limited predictive ability, you need more data to develop it rather than a model that has higher predictive ability.
I think that makes sense. It just means that, you know, if you have good predictors, a good predictive model, then you don't need that much data to develop it. Whereas
exactly, yeah, exactly.
A small but essential point that I think we should clarify. We've talked a lot about sample size, but we should clarify that it's not so much about the n number of your study, about how many people are in there. It's about how many events you have in your study. And that's, I mean, you touched on it when you talked about the smaller prevalence of the outcome. So if it's a really rare event, so you've got very few events, you're going to need a very, very large n number to be able to build a model on it. But it's going to be the number of events that determines essentially how good and how large your sample needs to be.
Yeah, and in that case, you need really good predictors, because you don't have the comfort of using many predictors because you have such a rare event.
Yeah, exactly. Yeah. So the idea is that if you have an idea about the number of predictors, the prevalence, and based on previous models, a ballpark estimate where the C index for that model would lie, then you can calculate how many patients you should collect data on. Okay, so here it's indicative. So that's based on 12 predictors. So on the left-hand side, we have prevalence 0.1. So, and then it's different assumptions about the C index or C statistic here. That's for binary outcome. So you can see that, say, for a weak model on the left-hand side for AUC around 0.65, you need around 4,000 patients, but you would only need 1,000 patients if you had stronger predictors that would correspond to a C 0.8 or higher. Okay, and then on the right,
just to explain to people, prevalence here means, let's say 10% had the event or 30% get the event. Let's say sudden death, for example. Yeah, sorry.
Exactly. Yeah. That's for binary outcomes, but it's similar ideas hold for survival. So on the panel on the right, you can see that the line has squashed towards smaller values, and that's because I have more events, and as Max said, unfortunately, it's the events that have the information in. So if I have a rare events like death in different types of cardiomyopathy, then it's the deaths that actually carry the information. So it's not only, we shouldn't be looking only at the sample size, but also the incidence or the prevalence of the disease. And here is another plot that shows, here I kept prevalence fixed, C statistics fixed, and I saw how the sample size would change with the number of predictors. So that is intuitive, because if I have more things to estimate, then I would need more information to estimate those things. Of course, if I include very strong predictors, then the C, as we said earlier, it will change. So I would need less sample size. So here it was an exercise where I kept prevalence and C-statistic AUC fixed so that I can check the effect of the number of predictors.
So practically, this means that you might have a lot of predictors in your data set, but you don't want to use all of them or many of them. You want to use what is right for your sample size, because otherwise, you will create a poorer model if you try to fit them all in.
Exactly. Yeah. So when selecting the sample size, we should think hard about the predictors, right? And the final thing, a little bit about so if someone has done a calculation, say for you, and it says, well, you would need 2,200 patients, and that would ensure that you get an expected calibration slope of 0.9. Unfortunately, that does not mean that if you collect a sample size of 2,200 and validate it in a good validation sample from the same population, you would get exactly 0.9, but you would get something around it, right? So the 10 dots here are 10 calibration slopes estimated from developing the model in 10 samples from the population. Say 1 point is Alex's study, the other is mine, then the other is Max, etc. So if you do it many times, then the average would be around 0.9. But if you look at your individual data set, then you are not kind of guaranteed that even if you have done everything according to the book, you will get a calibration slope of 0.9 when you validate your model.
So as you increase here, you can see that the average is about 0.9.
Yeah, the average is 0.9, and most likely chances you'll be around the average, but still, it's a sample, right? So still there are some because of sampling variability, you may end up you may have a sample that was not as representative of the population as you would have hoped, and that's happens with any sample. Now, the bigger the sample is, then the more representative of the population is, and the better, the less variability. So here is some options for calculating the sample size in case someone wants to look at that.
And listen, since if I didn't want to go down a rabbit hole of very fancy statistical estimation of sample size, I'm sure most of us have heard of the rule of thumb of 10 events for a predictor. So that the 10 events allow you to add one predictor to your Cox multivariable model. How accurate is that? Is that a reasonable estimation, or is it completely made up?
Well, Alex, if you go back 2 slides or 3 slides, a bit further, the one with the plots, the first plot that we have. Yeah, so this one. So imagine, Max, so I don't know, so for this case, the rule of 10 would draw a horizontal, say the left graph, right? Would draw just a horizontal line, and that would be the sample size that you should be using according to the rule of 10. So as you can see, what it doesn't take into account the rule of 10 is how strong you think your model is, right? So so you may end up, if you use it, you may end up with using more sample size than you should, or more likely you would end up with a smaller sample size than you should.
So I may be well underestimating my sample size.
Most probably, yes. So I would strongly suggest to use one of those calculators, because what you need to enter it's quite simple, really. It's something about the prevalence which you have, the number of predictors that you have. And in terms of the strength of your predictors, you can look at a similar model or a model that in a similar disease and enter that. So around 0.7375 is what we usually have in these cardiomyopathies. So of course that would depend on the particular disease, but and then that's it. You get a sample size that it would be better than the rule of 10.
Okay, but let's get you back to our variable selection then.
Yeah.
So how do we choose our covariates?
So we don't have a lot of time for discussion. So we need to be prompt with this. But this is one of the main things. We, especially in cardiomyopathies, we have more variables than patients. So are there? So one way I think is just to use what you think is clinically important. But are there any kind of more statistical ways of being able to select those variables?
So a very good topic. So yes, there are ways to select variables. By the way, as a parenthesis, I would say that the methods that for sample size and the number of predictors that I refer to assume that I have a pre-specified set of predictors. Right? So yes, there are motivations. Of course, I would a simpler model is easier to use, so it's better as long as it does almost as well as a bigger model. However, and there are many statistical techniques to do variable selection, but a warning is that every technique would come to with some uncertainty. Right, so you will never be sure that as you are dealing with a sample of the population, and usually the samples are relatively small, there is a danger of throwing a predictor that's actually good. Right, so if you do a variable selection, then you have to think very well, get a statistician. And there are some to help you with, and there are some techniques that help a little bit about the certainty or uncertainty we have about predictions being in the model or outside the model. Possibly, especially in small, for rare diseases, perhaps what we are going to lose from using a statistical technique and introducing uncertainty from variable selection will not be worth doing that. So in some cases, it would be actually better to get a group of clinicians that know well about the subject and get a set of predictors based on their experience and go with that. That would be a sensible strategy, definitely, especially for rare diseases or events.
I mean, there are so many, when you read through the literature, so many statistical methods where you can use, but I think, sometimes just selecting the simplest possible variables, the ones that are more widely available, because I can select, let's say, a variable that comes through a very fancy test that is not available to do in the real world. So, you need to be selecting variables that, are reproducible and they are widely available to be collected. So I think this is key. And kind of we can link this to the fact that sometimes if you select a specific variable, half of your patients might not have a value in it, because let's say in cardiomyopathies we put in a measure for that comes from cardiac MRI, something that patients with an ICD cannot have. That was a problem in the ARVC risk calculator. They used right ventricular ejection fraction, but when you try to validate, you don't have the data, and you have to extrapolate from another test like echocardiogram to be able to recreate that variable. So that makes it quite difficult. And you might have a patient that you might not be able to do a cardiac MRI because they're claustrophobic, for example. And I'll just briefly mention this because we're running out of time. But when you have a data set, imagine each row here is a patient, each column is a variable. You might have missing data here and there, and as I said, it's important to select variables that you wouldn't have that many missing data. And what you can do is either just delete from the data set the patients that have at least one missing data point, because you can't do the multivariable model with missing, at least the Cox regression model with missing data points, or you can estimate those missing data points, and there are various methods of doing that. We're not going to go into that, but I just want to ask Menelaos here, is there, because some people just think that if you impute a data set, then you're just committing some kind of crime.
Well, you're inventing data. It must be a crime.
What is the actual statistical truth
So
behind
you
that?
invent data honestly. That's what multiple imputation aims to do. So a few, just a couple of points. Complete case analysis. So we have to be very careful with that. And so complete case analysis may is sensible when we are, say, developing the model or validating a model. And having missing values means that I end up using, instead of 100% of my data, my rows, my patients, I end up using 95 or 90% of my patients. Possibly that would be a tolerable sacrifice so that I continue with the standard methods. Now, as this percentage of data that I throw away increases, then that increases the chances I get something that is wrong, so biased, or that is inaccurate. So for that cases, I should be thinking about filling in the missing data using an honest way, as I said. Multiple imputation. It is one way to do that, but we'll have to be. What Max said is actually a valid point, right? So I have to be very careful when I'm filling in data, and definitely in this prediction context should be done very carefully and with a statistician that knows about multiple imputation.
Absolutely. That's very important.
I also want to say some software even does that without even letting you know, right? Especially these machine learning softwares, etc. They might even impute and you have no idea, right? And they have done some unacceptable stuff and you don't know about that. So yeah, you have to be very careful when having some NAs on some dots in our data that correspond to missing data.
I think we might skip on machine learning. I think because we just don't have enough time to talk about it. What we wanted is to kind of maybe discuss some key clinical points. One that comes to mind, just before we go to the take-home messages, what comes to mind is we frequently have, let's say, the hypertrophic cardiomyopathy calculator model, and we keep applying it every year the patient comes. Although the model has been developed just with a baseline in the first 5 years. What is your statistical intuition regarding this? Is that a problem? Can it be a problem?
That's something that definitely needs some thought. Right? It sounds kind of like extrapolating the data, the predictions for the model, or using it for something that is definitely using it for something that it was not intended to be. So I cannot say how bad it can be. Possibly not too bad, but I don't know the exact answer to that. There are other methods that they make different types of predictions that could be used for that purpose.
Yeah, they did a study on the ARVC risk calculator, and they showed that at least for a couple of years the model holds. But the further you extrapolate,
exactly, yeah, that's
likely that you commit some kind of mistake. We have Professor Agostini is raising a hand. I'm just gonna give you the ability to talk, Luisa.
Thank you. My problem is with the last part of your presentation when talking about missing data. Suppose that I can complete a data set in more than one occasion, for example, in a couple of years.
Mm-hmm.
does this have the same value of the collection of data at the unique occasion? So I'm sure that I'm taking a picture of my patients with the complete data in a single occasion, or can I do it? I mean, if I complete my data in more than one occasion and in different intervals, does it influence the quality, the strength of the models or not?
I think
I think I understand what so you have, ideally you would you have a baseline where the patient gets diagnosed or comes in, and ideally the model says what are these cardiac measurements for the patient at this point zero, but you may not have it. So you're saying, can I do that when I can? I could be three months down the line or 4 months down the line, whenever the patient comes in, and use that for my model. So if that's the question, so that's not the best thing to do, but maybe it's a pragmatic thing to do. So if it's a measurement, say for the patient, that as you as a clinician know from experience that it doesn't change a lot, it doesn't change from month to month, then possibly that's a reasonable thing to do. But if you decide to do that and develop a model, have to clearly say that in when you write your work, because some other colleague may have different ideas about that. Yeah,
I think as we said before, I think the more you're extrapolating, the worse the worse it is. The question is, how do you find the balance between completely removing a patient and keeping the patient with some adjustments from imputation? But I think there is no kind of straightforward way on what exactly you can do and you can't do. I think you just need to be reasonable. And when you fill in the data, this needs to be only in a small percentage of the cohort. It can't be your whole cohort like this, obviously. Otherwise,
exactly.
It's just made
that's another
cohort.
point that I wanted to do. So first, if we have like half of the 50% of our cohort has missing data, that's possibly that situation we shouldn't be doing anything, or we should first exclude predictors that were not recorded, for example, some MRIs or whatever, and then left with whatever has a reasonable completion. And also, if a patient is missing almost everything, then also we're not going to impute everything for that patient, because that's quite risky. So sometimes we say if a patient misses 50% of the predictors, then exclude that patient.
Yeah.
So yeah, we'll have to be very careful when filling in missing data.
Whenever you read a paper and they say they've done imputation, I think it's a marker of quality of the paper, whether they do claim exactly how they've done the imputation and how if they have removed any cases. Exactly. Because in the real world, we always have those cases. And when you see a paper that doesn't say anything about it, then it's a bit sketchy, in my opinion.
Yeah. First we have to report missing data, and then how we dealt with missing data. Exactly. If it doesn't say anything, it's definitely something that we have to
So just to close the session, because you're running late, just a few take-home messages. I'm just gonna go through, and Max and Menelaos, add anything you might want. Risk models can be very, very useful. Can be practically useful. They can give us. It's an aid for clinical practice, but they shouldn't tell us what we should do. It's just an aid, and we need to have more education, more practice on how to actually use the models and how to discuss with patients. They need to be, developed using adequately sized samples, and that's why we spend quite a bit of time explaining the importance of sample size in the talk. You shouldn't just create a calculator because you have a few data. You should be very thoughtful about it, because if you publish it, unfortunately, people will use it. And the importance of both internal and external validation is so important. And you should never be using a model that's not been externally validated, in my opinion, unless unless there is some kind of specific reason. Very important is to apply the model within its scope. So if it was developed under specific circumstances for a specific way of specific disease, specific way of doing things, you can't extrapolate it into other applications. Let's say you can't use the hypertrophic cardiomyopathy risk calculator for someone who has left ventricular hypertrophy and doesn't have a cardiomyopathy. It doesn't work like that. It has to be the specific inclusion criteria should apply for your patient as well. And yeah, as I said, they just give you an estimate. They shouldn't be telling you what you're gonna do. Anything else from you guys?
No, I think you've summed it up nicely. And well, there are plenty of other things to dig into, but I think we've given a good overview today of the general issues and main points of discussion around risk modeling. So thank you both for running us through it. Alex for running the show, Menelaos for bringing some proper expertise to the meeting.
Thanks for inviting me. It was a pleasure.
And if anyone in the audience wants anything else to be looked into more detailed in the future, we can do further sessions on this. Thank you all for joining, and we'll see you in the next one. Take care.